Okay, this video clip we will be looking at vertical reduction formula, and as the word vertical indicates, we are going to bounce off the 90 degree 270 degree line on the Cartesian plane. But before we start there, let's remind ourselves of the basic trigonometry that we've learned, which was trigonometry in right-angled triangles. You learned that if I call this theta, now let's go back first. Triangle ABC, opposite angle A lies small side A. Opposite angle B lies B, indicated by a small b. Opposite C lies C, indicated with a small c. Folks, this is convention. Angles are indicated by capitals, sides by small letters. I say this is angle theta because that is 90. This will be the complementary angle of theta, which is 90 minus theta. So these are two complementary angles, meaning together they add to 90 degrees. Now let's look at what the sine of theta is and what the cosine of theta was, to remind ourselves. The sine of theta was opposite over hypotenuse, so it's C over B. The cosine of theta is adjacent over hypotenuse, and that is A over B. But I have another relationship that's A over B, and that comes from this angle. So if I want another A over B, I can say it's the sine of this angle. Sine of that angle is opposite over hypotenuse. So it will be the same as the sine of 90 minus theta. And the same here with C over B. C lies adjacent to that top angle. And then if I say adjacent over hypotenuse, it will be the cosine of that angle 90 minus theta. That comes from our right angle triangle. So the angles are complementary, and look at this now. We're going to call these ratios complementary. Sine is the complementary ratio to cosine, and cosine is the complementary ratio to sine. So it works in both directions. Okay, I hope that made sense. So let's go to our Cartesian plane. If I draw an angle in here, a terminal arm, and I want to express this angle as a bounce from this vertical line. Okay, then what do? I go 90 degrees clockwise. So the 90 is positive. Then I bounce back. Let's call this alpha degrees for now. Okay, I bounce back alpha degrees. And notice I put a minus because I'm changing direction. We learned that if we go clockwise, the angle is negative. If we go anti-clock, the angle is positive. Now remember, we know that alpha plus theta are complementary angles. So theta can be expressed as 90 minus alpha. The algebra here confirms exactly what happens on the Cartesian plane, folks. Exactly the same thing. Now if I reflect like I did before, that terminal point in the y-axis, okay, then I can see it as this angle has repeated over here like it did for horizontal reduction. But to get to that angle, I can now go clockwise 90, and then I bounce on alpha degrees. So in this quadrant, I went clock to 90 and clock to alpha. I didn't change direction. So all angles in the second quadrant over here, expressed as that vertical line, is expressed as a bounce on from the 90. Okay, now if I reflect that same point here, in the x-axis. I come down with it, I reflect it. It's more or less in this position. I join with my origin or my center point over here. Okay, we say that is the terminal position for all angles, is the 0, 0 position on the Cartesian plane. The language, terminal position. Okay, so let us have a look at then what has happened. First of all, my same idea brings a theta in at that point. But because I'm bouncing off the vertical line, I'm going to express this as going all the way around, going to 270 degrees. I went clockwise and then I bounced back alpha. Why alpha? Well, geometry tells you those two lines are straight and they intersect at that point, so the vertically opposites are equal. But this is in a negative direction. So if I want to express in terms of the vertical line, express my angles in third quadrant, I express them as 270 minus alpha. And again, by the same token, if I now go and I reflect this point in my x-axis, I more or less land up there. I join the two, and again on this position I will have my theta. This time around I'm going to do the same thing, but I go to my 270 line and I bounce on alpha degrees. So I've moved anti-clockwise 270 and I've moved a further alpha degrees in the same direction. Okay, now that is important, folks. So in my fourth quadrant lies here, my first quadrant here, my second here, and my third quadrant lies over there. We also have, remember what we arrived at in terms of the sign, positive or negative of the angles, my cast diagram. Okay, so cos is still the only function that's positive in the fourth, tan is still the only one positive in the third, sine in the second, and all of them positive in the first quadrant. But now, because I'm working with the 90 and the 270, angles are complementary. Therefore, I need to bring in my complementary ratio. So these two angles are complementary angles, and my ratios, as we indicated here, are complementary. We call them in short co-ratios. The co stands for the idea of complementary. So we saw in this triangle, the sine of theta became the cosine of that angle. The sine of this angle is the cosine of the complementary angle. Okay, so if I start talking about the angle cosine of 90 degrees plus alpha, I need to say to myself, first of all, I need to acknowledge the fact that there's a complementary angle involved in this. Okay, we call that a complementary angle, and because there's a complementary angle involved, we need to change this to its complementary ratio. Okay, and then the cosine of 90 degrees plus alpha will then be the sine of alpha, first of all. Secondly, in the second quadrant, which is where 90 plus alpha would lie, only sine is positive, so cosine will become negative in that quadrant, and there you have successfully used your complementary ratios, your cast diagram, and your vertical reduction formulae. Okay, so wherever there's a 90 or a 270 involved, we introduce our complementary ratio. Now let's try and break away and break free from that diagram, and let's see how this works in real life. I ask you, what is the sine of 90 plus theta? Or I can ask you the sine of, let's start in the first quadrant, 90 minus theta. Now you have to read everything that you've learned so far. You've got to absolutely draw on that. The first thing you learned about was your vertical reduction formula. 90 minus theta, first quadrant, because it bounced back. 90 minus alpha. So 90 minus theta will be in first, 90 plus theta will be in second, 270 minus theta will be in third, and 270 plus theta, it goes 270 plus something is in the third quadrant. Okay, and indicate your cast diagram over here. So now you interpret. Fine, let's cover the ratio. 90 plus theta, you ask yourself, in which quadrant am I? That's the first question. Then you identify, fine, I'm in quadrant 2. Then you ask yourself, what happens to the ratio sine in the second quadrant? And it is a positive in the second. Then you say, what is happening to sine because of the complementary angle? It becomes the cosine of the angle theta. You bring in your complementary ratio. The same here. 90 minus theta is 90 minus theta. It's in my first quadrant over here. What happens to sine in the first? Well, according to the cast diagram, all ratios are positive in the first quadrant. So sine will have a positive sign, meaning positive or negative. The sine ratio will be positive in the first quadrant. Because I had a 90 in here, I am working with a complementary ratio of the complementary angle to the theta angle, which was in my right angle triangle. Look at that. The sine of theta is the cosine of 90 minus theta. Okay? Sine of this angle is the cosine of that. Or the sine of that angle will be the cosine of this angle. And that's what we're working with when we work with 90 minus theta. This angle is not in the triangle, or it could be in an obtuse angled triangle. So a triangle that looks like this. We have a right 90 degrees there, and then we have a theta degrees onwards. But it's impossible here to talk about my complementary angles because it's not a right angled triangle. So it's rather better, therefore, to look at it as where it lies on the Cartesian plane. So very important. If you work with a reduction with 90 and 270 in it, you have to, in your head, ask you, which quadrant is it in? What happens to the trig ratio in that quadrant to determine the sine? And then say sine, because of the 90 or the 270, will turn into the cosine of the acute angle that you have calculated over there. Okay, folks, I hope that that made perfect sense for you. Please note that the easiest way to look at this for yourself is to work out which quadrant you are in, drawing these small diagrams showing what the sine is, and then remembering that you are working with your complementary ratio.